Daniel Feijó, and this is Physics 1 Lab 4 on oscillations. We analyze a mass spring in gravity that both stretches and swings. The aim is to compare a real recording to a computer model and explain agreements and differences using basic physics. What will be covered in this lab presentation? The introduction, models, experiments, coding, data discussion, and conclusion questions. We will define the purpose, list physics principles, describe our setup and tracker workflow, show the simulation, compare predicted versus observed motion, plot energies, and answer the energy principle and period questions. So the purpose was to study an object moving under a restoring spring force and gravity and see how that creates oscillations. We compared the observed motion to a model based on Newton's second law and Hooke's law to decide if the total energy is roughly constant and whether the period matches theory. The model and observation follow similar curved paths and timing. The model is smoother because it assumes an energy ideal spring and minimal losses. The observed data shows small amplitude decay and jitter due to dampening and measurement noise. The physics principles explain Newton's first law, inertia. Motion stays as is unless a net force acts. Newton's second law, momentum principle. Net force changes momentum. Here, the force equals the force of the spring plus the work. Hooke's law shows that the force of the spring equals negative KSL, with stretch S equals L minus L initial along the spring direction L. Energy E equals kinetic plus the potential of the gravity and the spring, which equals 1 half mv squared plus mgy plus 1 half ks squared. If external work equals 0, total energy stays about constant. These explain why the mass speeds up near equilibrium and slows during turning points. The steps of the lab. We recorded the motion, calibrated pixels to meters with a meter stick, and tracked the mass frame by frame to get xt and yt. Y2 coordinates because the spring's direction rotates, so a single axis would miss parts of the motion. We exported positions versus times for plotting and for estimating velocity and period. The steps of the lab, the code. The computational model used the same initial position and velocity as the recording. At each time, compute L hat. S equals L minus L initial, and L hat. Apply forces F equals negative KSL plus 0, comma, negative mg, comma 0. Update momentum and position. A small t matched the video frame rate so the curves align in time. We use an energy-friendly update so total energy drift is small. Comparing predicted motion and observed motion of mass. Predicted versus observed paths overlay well. Both show a curved trajectory due to radial tangential coupling, stretch plus swing. The observed track is noisier and the amplitude slowly decreases. Likely causes light air drag and internal friction, small miss estimates of K or L initial, camera perspective, and cursor pickoff error in tracker. Plotting energy changes from computer model. From the model, spring potential is larger at maximum stretch. Gravitational potential energy is largest at the top of the motion. Kinetic peaks as the mass passes through equilibrium. The total energy line is almost flat. Small drift means small losses or numerical error. This is our main diagnostic that the model and parameters are reasonable. What does it mean? Is the energy principle satisfied? Yes, within measurement and numerical limits, total energy is approximately conserved. Gravity and an ideal spring are conservatives, so they only exchange energy internally. Any slow decline in total energy suggests a small dampening force. Adding Fd equals negative BV in the code would reproduce the observed amplitude decay. What does it mean? Estimates of oscillation periods through x and y data. Estimating t from xt and yt can give slightly different numbers. Reason each axis is a projection of the 2D coupled motion. If stretch and swing are not perfectly in balance, perfectly in phase, trough to trough, timing shifts a bit. Taking multiple cycles or fading reduces this bias. What does it mean continued? Theory says small vertical mass spring oscillations have t equals 2 pi square root of m over k. Our setup swings and stretches, so geometry and gravity's tangential part modify the effective restoring action.